Yeah, so you don't need to know what the wave function is, just know that it exists, and that's how we calculate probability of where the electron may be. And again, two things: you can't know the position or the velocity at the same time. You can know either or. Thus, you can only predict a certain region in which it can be. You can't predict where it exactly is.
Right.
Okay.
Thank you.
That makes sense. And keyword Heisenberg uncertainty principle.
So does that make sense to everyone? Sort of. Quantum operations are weird.
It doesn't make sense. It's okay because it doesn't make sense to most of us.
Yeah, there are like I think 12
physicists.
people in the world who it makes sense to.
Yeah. So if you think it makes sense to you, you're either lying or you really don't understand it.
Makes perfect sense. So moving on, there are more orbitals than just S and P. There's more complex shapes that you can have. So the next layer is d orbitals. And they have 5 for a total of 10, 5 orbitals for a total of 10 electrons to be held.
And they look really weird.
Yeah.
Don't bother drawing. They're just to confuse them.
Don't they look kind of like
anyway?
It's
that?
3D, so
Yeah, they're a little
Isn't it?
complicated. Like, look, I'll show you. Show what they
Yeah, Osman will draw.
No, like that's what they look like. Like there's D sub.
That's really stupid.
Yeah. So I can show you. So
Yeah,
okay,
could you draw that
so
while I'm explaining?
assume a three-dimensional space, right? We have a z-axis, a y-axis, and an x-axis, right? Okay, so you
Because
have
that's alphabetical order.
depth, height, and width. So yeah, just like completely opposite. Okay, well, earlier on we talked about our first orbital, our spherical orbital, right? And we just have one of those. That's just a sphere, like that's the s orbital. With our p orbital, we have 3 types. We have that dumbbell shape across the x-axis, across the y-axis, and across the z-axis, right?
And it takes a little bit more energy to make that complex shape.
Right. So it's like
So-
that dumbbell, like this, that, and like that. With your d orbitals, it gets a lot more complicated, and so it looks like, so for the first one,
It looks like 4 blobs spread out in one plane. And that's true for 5 of them, I
Yeah.
think.
so
Until you get to the last one,
it's like a
which
donut.
is, yeah, it's like one of the p orbitals, but it also, there's like a donut of high probability around the center, perpendicular to the axis that the dumbbell goes through.
It's kind of like what it looks like right there.
So these are,
You'll probably not be testing on
these
this.
are orbitals.
could you
So
guys
this-
use a darker marker?
It's not. It doesn't make sense if you can see it. It
Okay.
really will help. It's basically. I understand that
Black markers
this doesn't mean that your electron looks like a four-leaf clover. It just means that your electron can exist in this region based on the particular characteristics of that orbital type. So d orbitals look like that, and then you have that donut. So they'll ask you like they're not going to ask you this like any test, but maybe the state test, and that gets more complicated. So we're only talking about the basics right now. Okay.
And then just beyond the d orbital, with higher and higher energies, still within the same energy level, you get the f orbital. So where all these are filled, anyone can pull up a periodic table. Osman, can you go through that book, hold up a periodic table or something?
There's one right there.
Okay. Oh, you can see up there.
And
I'm going to walk over here. So I'm...
The F orbital is so complicated in shape that
It's
the book
not
doesn't
even
even
worth
bother
it.
drawing it at all. So
It gets pretty abstract, and these complicated shapes are why it takes more energy. So, looking here, with counting the electrons from left to right that get filled, at the first energy level, there's just an s orbital. So it will be filled 2 electrons. So that's the first energy level. It's done. So on your Bohr model, that's why there are only 2 electrons in that very center ring. Then on the second energy level, you get a total of 8 in the row. So there's 8 valence electrons in that outer ring. So you get 1, 2 s orbitals, 1, 2, 3, 1, 2, 3 in the p orbitals. So you kind of get a block over here of all the p orbitals, and you get a block in these first 2 rows with the s orbitals. And because of the order of orbital filling, some people want to say helium should be over here in the 2A group. Thank you. This is a ruler. This is not an eraser. still kind of unnecessary. Anyways, so you get kind of an S block here and a P block here, in the sense that that's where elements are that fill up those orbitals when they gain an electron. Then in the transition metals, when you get an increasing number of electrons in the atoms, you get an increasing number of filling up the d orbitals. So there are, expressed by similar chemical properties, there are 2 for the S block and 6 for the P block. And so there are 2 columns and then 6 columns here. This transition metal area has 10 columns because there are 10 different electrons that can fill those orbitals. And when you get down to the transition metals, there are 17.
14.
17? Okay, 14. Excuse me, I didn't get much sleep last night. 14 open spaces for electrons to fill, and the f orbitals, so there are 14 columns.
Now, recall that we had how many orbitals in the S category? How many S-type orbitals?
Here's a hint.
One.
Easy question.
1. That's team 1.
One orbital.
All right.
Yeah.
Two
How
electrons.
many electrons? 2 electrons, right? How many electrons can be in one orbital?
2.
2.
Yeah.
All right. Team 2, step it up. Come on. All right. Well, based on that, we have 1s for 2 electrons, 3p for 6 electrons, 5d for 10 electrons, and 14f for 7 electrons. So if on a test you get lost and you're like, oh shoot, I forgot how many orbitals there are in this d sublevel, then you can just count 1 through 10 and divide by 2. 14 by 2, 6 by 2, and 2 by 2.
It's increasing odd numbers.
Yeah.
So you get S, P, D, F.
1.
And I haven't found a good mnemonic for it, but it's just 4 letters. If you can remember that order, think spherical first, and then the rest of them come after.
Number, spit it.
Some people
Split it.
demand freedom.
That's pretty good. Some people demand freedom. Smart, can you write that down while
Yeah.
I go on to cooler things?
Some people demand
Not cooler relative to what you said. Cooler relative to what I've been teaching. So, do you recall how the oxygen atoms, when they reacted, there were bonds that formed between them? Any reaction whatsoever?
Come on. Yes.
Heads nodding?
Oh.
Yes. The losing
Yes.
team doesn't get popcorn, and the winning team gets cake.
So it's the person demanding freedom. So you remember that these orbitals will move from instead of orbiting the atom and then orbiting the nucleus, they'll instead start orbiting between the two, kind of like a comet orbiting 2 suns or something like that. And you get these bonds formed between them where there are orbitals of electrons sharing these orbital spaces. And what eventually happens is you count this with what's called Vesper theory. And the name is kind of a misnomer. It's actually VSEPR. It's just a lot easier to say Vesper instead of Zepper. You know what I mean?
I know talking about Jack.
No?
Zepper.
Zepper.
Kidding.
So the simplest hybridization, they call this hybridization of bonding.
Because you form a hybrid when you take 2 pure orbitals together, so that's where that comes from.
Explaining the foundation before I explain the details. When you have a core, like one atom, and then atoms bound to that, that's what Vesper measures. It'll start measuring the shape of what forms. So O2 is really simple. It's a straight line. And we count it as, there's one place where there's a bond. So it'll have it's bonding with an S.
Oh, Jane, can I go into this? Never mind. Oh, are you?
Oh, do you want to go into this later?
Yeah, and I was going to go into the shapes, and molecular shapes and stuff.
That's what this is.
Yeah, I thought I was going to do molecular. It's okay, we can
Do you want to do this?
do it together or something. Or you want to explain the theory, and then I'll go into shapes? Specific shapes?
Yeah.
Okay.
So the idea is that as you add atoms, so we're going to add atoms here, there's big clouds of electrons all circling those atoms, and they want to repel. So there are repelling forces between like electrical charges, and they'll all just kind of push themselves out to the side. so they're not interfering. So here we have one particular arrangement where there's one core atom binding with 1, 2, 3 atoms, and they will push themselves out to make a triangle. And it's pretty simple, but what gets complex is when you start having non-reacting orbitals. Let's give you a case with water, the simplest example of this. So you're going to have some oxygen atom and 2 hydrogen atoms. And most of you, at least since freshman year, should have seen pictures of water as being bent. The reason for this is that oxygen has, in addition to orbitals extending to the hydrogens, has 2 orbitals with filled pairs of electrons. So in 3D space, they will want to spread out as much as they can. So you end up getting a shape that looks kind of like that. So all of your electron clouds are pushed as far away from each other as they can get. Does this make sense? And only 2 of them are visible because only 2 of them have atoms. But those electron orbitals are the charge bits that are actually repelling. So with all of this, you get a tetrahedral shape from the spokes of the directions of where they're going. But you end up with just a bent shape of the atoms you can see. And from that, we get all sorts of really funky arrangements that my friend and colleague Osman will now cover.
Okay, I'm excited about this. Alright, I'm going to erase this up here just to make it a little clearer.
He's going to be all over this like tasty and popcorn.
Which some of you may not